Welcome to the second day of our meeting. It's my great pleasure to present Vitor Matos from Portal University, and he will talk us about non-local solutions in conservation laws.
Thank you, Gregory. Well, it's a pleasure to me to be here to present my work to you. Actually, I will present a 10 years old work, but some results that we can achieve with this primary result that has already 10 years. Well, our framework is a system of two conservation laws, and I will talk about some waves and the curves that represent that waves in the space state. And I will use something similar to the RP program, and the one rarefactions are in blue, two rarefactions in red, one shock is like this, two shock is red, overcompressive it's in yellow, and a transitional, well, here actually this is not a really transitional wave, it's more a cross shock, because usually this kind of shock has no viscous profile, but I'll be a little bit loosey in this nomenclature. But what I'm looking for is for the left and right characteristic shocks. For instance, the left characteristic shock of type shock 1, it's in the middle of a branch of a one shock and a transitional shock, or crossing shock, if you wish, and so on. First, I will tell you that we have 8 left characteristic shocks, but 2 of them, the transitional characteristic shocks, usually have no viscous profile. So actually we have only 6 cases to study. Let's start with the right ones. Well, this is a classic result from Bettwendorf, and you will see about 10 years ago you use it to construct some non-local solution. Well, what Bettwendorf tells us, when we have a characteristic shock with or what is a characteristic shock? It's a shock where the speed equals the characteristic speed of this point. Well, here we have a one shock curve, and then we can go on with a rarefaction. It's a classical result. With the 2 shock, it occurs exactly the same, and this is quite standard. But we have also a third one that is left characteristic shock of overcompressive type. And this shock is in the middle of a overcompressive shock and one shock 1. So what happens with this case? Actually, this situation is also quite usual to see. Let me put here the Hugonot curve from this point, L, and suppose that we have a state N such that the shock from L to N is right characteristic there. Well, usually, despite the Hugonot curves are not a foliation of the plane, usually we have some Hugonot curve that cross that point, starting in another point here. Well, but by a simple law that is a triple shock law, we know that this shock is also a characteristic shock, is a 2 shock, right characteristic 2 shock, so this is not a good representation of the Hugonot curve, since this Huguenot curve that starts in M also must be tangent to the characteristic field. So we have this configuration. Well, as we know from this case, here, this one, from here, we can have a rarefaction. So actually this case is the limit case of this one. So we have just a shock from here to here, and then a shock from M to N, and then a rarefaction, or directly from L to N, and then a rarefaction. So these two cases go together. If you choose another M above this one, we have this. If you choose another M below this initial M, this two shock stops here to be compatible. So this part, even having a viscous profile, is not compatible with this first shock. So, oops, sorry. The only part that appears in the solution is this one. Since this is a maximum of the speed, you have a speed here and another in this side is exactly the same. So by the triple shock law, we know that we have a shock from here to here that cross there, and we have this configuration. This is a classic one too. But here we will call it the basic one non-local solution. Well, this is just a result that depends on Betwendorf and triple shock law. It's easy. Well, the result I will show you is a theorem where we prove that the composite curves are envelope of Huguenot curves. Let's pay attention now to the left characteristic shocks. Well, the left characteristic shocks, you have three kinds, and two of them are quite usual. This is the left characteristic one shock, so we have something like this, to one shock and transitional shock. And our theorem tells us that if we move the point L to M over a rarefaction, all these points here that forms the composite curve are the envelope of the Huguenot curves. Actually, this is not what you usually see. You usually see, okay, this is the envelope, is the joints. Okay, another thing. And you can prove that the Huguenot, the envelope joins with this Huguenot curve smoothly with this branch that is one shock. And with the transitional shock, they go like a cuspid. The same occurs for the two shock. If we move the state M over a two rarefaction, all these left characteristic shocks form an envelope of these Huguenot curves. But what usually to see is something like this, not in this configuration. That is, we move on the one rarefaction, and the curves, it's not so easy to see like here. So it's a reason why I show this here. But this point has a Huguenot curve here with transitional and one shock. This one has the same one shock transitional. And if we move here, these Huguenot curves form an involutory, and this involutory is the composite, one composite curve. The same occurs in this case. Well, the fact that this is an involutory allows us to prove some things that we'll show you in a few minutes. Well, but we have a third case of left characteristic shocks with viscous profile. That is a overcompressive one. Well, in this case, we have an envelope of the Huguenots, and they join smoothly with the overcompressive part, and with the two shock part, it forms a cuspid. There is another thing. Okay, it's all. Well, how we see this configuration in the solutions? Actually, what you see is something like this. If we move this point over one rarefaction, we have an envelope that joins smoothly with this part, and then we can reach this interior region from this rarefaction. We only can reach this part here that has a shadow, and this one is not possible to reach from there. Okay, and I call this configuration a basic to non-local solution. Well, what this allows us to do? First, let's start with basic to configuration, this one. So we can reach this point here from the rarefaction, since this is an envelope. Well, usually the one rarefaction reach an inflection, or at least it could reach an inflection. So if it reach an inflection, we have one composite curve from this side. So we have here again the triple shock law, and you know that from here to here we have a left correlative shock with the same speed like of this one, and then we have here this configuration. If we continue this till the left characteristic shock from L to prime L, we have this. But if we are in a general situation, L is in the hyperbolic region, so we have a one shock for the other side. If we have a one rarefaction to the right, we have one shock to the left, and here again we have the triple shock law, and we have this configuration. Here the three curves are transversal, and here not. This one is tangent on one side, and in the other side this reach there, forming some angle that is not zero. Well, this structure, we call it the fishbone structure, and this fishbone appears in a lot of situations. Some years ago, with Pablo Castaneda, we classified the umbilic point in the triangle of the saturations for fluxes where each flow depends only in its own saturation, but this power could be something greater than 1, even rational powers here. So we prove that we have another triangle here where inside the umbilic point is type 1 and outside is type 2. And then some years ago, we also studied how the solution changed from the type 1 case to a type 2 case crossing this border. Well,
what's that border?
Okay, it's a border between the type 1 umbilic point and type 2 umbilic point. If you choose these powers, yes. So if these powers are all of them 2, this triangle is exactly a triangle that fits in the middle of the big one. But in a general case, it's a tethered triangle here. Actually, this work was made for the power 2. And we have solutions like this, and almost all the solutions have 3 fishbone structures at the corners of the total solution. So, as we know that this happens, you can rule everything in a nice way and in a general one. It's not a particular case. It's something quite general. Well, let's keep googling some structures. Well, if we start with a rarefaction, then one composite, and this one composite curve goes with one shock smoothly, and then let's this one shock go with the composite shock here. So if this happens, they go here, and then we have here the structure B1. Here we have the two kinds of right characteristic shocks, and this go like this. Well, this is exactly what happens with the type 2 quadratic problem with the elliptic region. And studying this type 4 case of quadratic fluxes in 10 years ago, we proved that we have high amplitude solutions for really small initial data. We can choose these 2 points as close as we wish, that the solution always needs to go there, and this is always something greater than 1. You need to go there to reach this point. And the key to show that we have no local solution is that this is an envelope. So, yes, this is an envelope. So we can reach this point inside the envelope from the one rarefaction. So the fact that this structure is actually an envelope, it was the key to show that we have high amplitude solutions for small amplitude initial shocks. Well, this viscous profile exists for viscosity matrix equal to identity. But if the viscous matrix is not identity, the Mailybaev instability region isn't anymore the elliptic region. So it's not so easy to show that the viscous profile exists. But numerically, with Gustavo Heim, at least numerically, you see that this solution is probably it occurs also for another viscous matrix, but it's not a proof. But at least we have a numerical indication that this keeping to occur even for non-identity matrix. Okay. This is something that could be quite general. Here we ask for elliptic hyperbolic region. There are not a lot. We have no greater codimensional things occurring here, but sometimes we have flux that are not generic. So they keep some structures that, if you perturb the flux in the free way, don't appear. But if we change our flux in the class of fluxes, we can have some things that are not generic, but they are stable, and we can perturb the initial data, and we keep seeing the same, but we can perturb the flux. If you perturb the flux, the things disappears, but we can perturb the initial data. Another non-local structures is the Latin sail that appears in the models of oil exploitation, and it appears when we have a bifurcation here. So this is the diagonal curve from this point. We have a bifurcation, and all of these transitional shocks have viscous profile. This is not generic if you perturb the flux, except if you perturb in a certain way, just in the family. Well, if we have this, we have shocks from M to any point here, and then by triple shock and things like this, we can prove that we have a solution that forms this triangle. This is the reason why we call it Latin sail. This is so another non-local solution that resists the perturbation of initial data. We can move a little bit R and L, and we still have this configuration. Another, 1 minute, okay. And another kind of fluxes that are not generic was studied with Júlio Daniel Silva, that are systems where some composition, chemical composition, adsorption, so some kind of these models that have Huguenot curves that we can move M and we have always this configuration. So this is also not general, otherwise this bifurcation will broke. If we go up, this make something like this, we go down, this should, oops, sorry, split. But in this kind of models, this cross is persistent. And in this case, we have solutions that one rarefaction goes with a two rarefaction without intermediate state. So they form only one wave, and we can move L and R, and you still have only one wave in the two-dimensional system. So that's all. Thanks.
To ask you about the non-identity viscosity and the numerics. So you've got a nice solution with a similar structure or different?
Yes, we tried some viscous matrix, some of them not so close to the identity, and you're still seeing the same, even with a larger Mailybaev instability region, but we have no real conclusions. We try to understand the problem, and we only get that, okay, it could be stable even with other metrics, but we stop there.
So you don't have a picture of all the waves and so on, but you can see a nice solution when you
here I haven't, but if I look for things from 10 years ago, I'm sure I have it.
What's the role of the overcompressed? It's I tell everybody to ask you, so now I am asking you.
The overcompressive?
Yes.
Okay. They appear here, joining two solutions, one from this part and another from that one. And here it's the same, but it's not anymore the overcompressive branch of this Huguenot curve, but is the continuation that occurs from this envelope, and it works exactly in the same. They split two solutions.
With overcompressives, I recall that you have many different profiles that connect to end states.
Yeah.
How is that selected numerically? I mean, do you see them all or only certain ones?
Actually, from here to here, and then to get this point, with a Riemann problem with this left point and this right point, we have two solutions from here and from there. But actually, all these shocks have the same speed, so we see the both in the same place. So we can recognize it in the numerical simulations.